Okay, hello everyone. I'm Yifan Yang from Tsinghua University. I will introduce our work P4runpro, enabling runtime programmability for RMT program switches. The other authors are from Tsinghua University, Zhongguancun Laboratory, and Alibaba Cloud. So first is the background. For the current RMT switches, there is a single data plane context defined by P4. The programmable switches becomes a fixed function switch after the binary image installation. If we want to add a new function or program to the data plane, we must suspend the traffic and reprovision the switch. This is not friendly to the P4 programs and the network operators. For the programmers, they want to run unrelated programs separately, and for the operators, they do not want the traffic to be interrupted. However, we observed that the programs on the CPU architecture do not face the problem because they have the operating systems. What they only have to do is to craft their programs using high-level languages like C and CPP, and the hardware is not visible to the programs. The OS provides us with compilers to translate our programs to binary code, maintain processes, and automatically manage the CPU cycles and memory for our programs. So can we build an OS-like layer between the programmer and the RMT switches? Ideally, the OS-like layer can provide abstract programming interfaces for the programmer and automatically allocate the hardware resources for programs at runtime. The RMT programs only need to code, and the switch only need to be reprovisioned once with the OS-like layer. There are lots of related work about this to achieve runtime programmability. The first type seeks for new hardware architectures. They utilize FPGA or DRMT switches to enable runtime programmability. However, their solutions cannot be ported to popular RMT switches. The second type virtualizes the data plane tables and supports runtime program reconfiguration. However, their solutions are extremely resource-consuming and cannot be deployed on hardware targets like RMT switches. The third type is dynamic resources. LetVRM enables dynamic memory for the RMT hardware, and Newton and Flemon enables runtime reconfiguration of similar programs. However, they only support a set of pre-configured programs, lacking generality. Active RMT and switch VM enable runtime programmability on the RMT switches. However, active RMT can only be deployed in an active network where the program is attached to the header, and switch VM also has similar problems and wastes nearly half of the memory in the pipeline. So to bridge the gap, P4runpro enables general runtime programmability without any exception for the coming package. Our key idea is that we can decouple the switch programs into pre-defined atomic operations at compile time, and then after we provision the switch, we can dynamically allocate resources and combine the atomic operations into switch programs at runtime. Our architecture has three parts. The first one is the data plane. We build our data plane pipeline with a one-shot compiled P4 program. The pipeline has an initialization block, several runtime programming blocks, which we called RPB, and a recirculation block. The RPB is the general program execution unit that can be perform atomic operations. Second, we provide a set of programming interfaces we call P4runpro primitives. In addition to the interfaces and hardware pipeline, we also build our control plane. This control plane can compile the P4runpro primitives, manage the hardware resources, and download the program to the hardware. Through this, the program only need to craft their P4runpro programs using the primitives and input them into the control plane compiler. They do not need to care too much about how the hardware works, and the control plane automatically deploy the program to the data plane. So here comes the first challenge. How do we build a one-shot compiled P4-defined data plane on the resource-limited RMT switches? Our solution is to virtualize the resources, including the stateless PHV, stateful memory, and the computing units. For the PHV, we designed several registers in the PHV. Their values are extracted from the header or metadata and can be used to modify the header or metadata. For memory, we use a mask-based address translation mechanism to virtualize the physical memory, allowing the memory to be dynamically allocated at runtime. For the computing units, we predefine a set of atomic operations. They can operate the registers and virtual memory, completing the packet processing logic. For the specific process of program execution, when a packet comes, it goes into the initialization block first. In the block, we track its passing path, use a bitmap. Then different bitmap values will trigger different filtering tables. The filtering table will distinguish the packet type by matching the head fields and assign its program by setting a flag called program ID. Then the packet goes into the RPB sequentially. We have three program control flow flags called program ID, branch ID, and recirculation ID. The program ID is used for RPB to distinguish the current program for the packet. The branch ID is to distinguish the current conditional branch, and the recirculation ID is to distinguish the current recirculation iteration. Before real execution, the RPB will first check the three flags. If the RPB matches the three flags, the RPB will execute one primitive. The primitives in a dependency chain will be sequentially executed by RPBs. For a special primitive we call branch, the RPB will additionally match the values of the registers and make the program go into a different conditional branch by changing the flag branch ID. After the branches, the primitives in different branches will be executed in parallel in the same RPB according to the flag branch ID. Then, after all the RPBs are executed, the packet arrives at the end of the pipeline. Here comes a problem. We have limited RPB executions, so we utilize the recirculation function of the switch to enable the programs with longer dependency chains. If the program does not end after the packet arrives at the last RPB, we recirculate it to the first RPB to continue the program execution. We use the flag recirculation ID to track the process. Now we have prepared the data plane. The next we need is to provide the programming interfaces for the programmers. However, the limited VLIW instruction resource means that we cannot predefine too many atomic operations in the switch. So our solution is to compress the primitive set and design the pseudo primitive. First, we compress the primitive set based on the observation that many switch programs can be divided into a combination of 6 types of operations, including header interaction, hash, conditional branch, memory, arithmetic and logic, and forwarding. Then we design the pseudo primitive to support more general programming. The pseudo primitive is similar to the pseudo instruction in the symbol language. A pseudo primitive is equivalent to a primitive when programming, but replaced by one or more primitives for hardware execution. For example, we can provide primitive 8i for programmers and implement it by actually executing load I and 8 in the hardware. Okay, now we have both the programming interfaces and the virtualized hardware, we still face the challenge of how to link the program to the hardware. So we built the P4runpro control plane with the main component of the P4runpro compiler. The compiler can automatically parse the programs, allocate resources for the programs, and consistently update the data plane. When we invoke the compiler to compile a program, for example, a catch program detailed in the paper, the compiler first performs a syntax and semantics check, and then generates the AST. Each primitive is a node, and each dependency chain is a subtree in the AST. Then the compiler will add the address translation and pseudo-primitive translation steps. For time reasons, we do not go into detail about this. And then the compiler performs a location scheme, which is formalized into a SMT problem. It is a first come, first serve, and best effort scheme, and it will determine which RBP to execute which primitives. During this process, the memory and table entry resources of the data plane is automatically allocated. The last step is to update the data plane. We face the problem that if we update the data plane with the traffic running, there may be some undefined or unwanted behaviors. Fortunately, we can utilize the control flow flag program ID to ensure the automaticity and consistency of the data plane update. If we want to terminate a program, we first delete the single entry of the filtering rule. Then all the subsequent RPBs will stop at the same time, since there will be no more packets assigned with the corresponding program ID. Similarly, if we want to add a new program, we add the filtering rules after all other rules are ready. That's all the design, and we implemented our prototype on an Intel Torfino 1 switch. We implemented 20 RPBs with a table size of 2K and a memory bucket number of 64K. Then we use the prototype for evaluation. We evaluate P4runpro first in generality and expressiveness. We use P4runpro primitives to craft 15 runtime programs. These programs can be deployed and revoked at runtime without restarting the switch and pausing the traffic. We also compare their simplicity to the original P4 programs. The results show that P4runpro can express P4 logic using a smaller number of primitives. We then compare the data plane update delay to active RMT and fly mode. Most of the programs can be updated in 14.1 milliseconds and is faster than active RMT and fly mode. Then we compiled our allocation delay to active RMT. We continue to deploy programs and use the four workloads: the in-network cache, stateless node balancer, heavy hit detector, and a mix of them. We find that our allocation scheme can find the solution in 400 milliseconds, regardless of the resource distribution of the data plane. Then we evaluate our memory and the table entry utilization of the four workloads. We find that P4runpro can achieve a average 65 to 80% resource utilization. We then add two new workloads, the program net cache and all mixed of the mix of all the 15 programs. We evaluate the program capacity of how many programs the data plane can support concurrently in these workloads. We find that P4runpro can enable a maximum of 2.8K programs for the workload load balancer and 77 to 123K concurrent programs on the workload or mixed. At last, we conducted several case studies to prove that P4runpro programs have the same functionality as the corresponding original P4 programs. We start deploying these programs at the same time. Our results show that there is nothing different in functionality of these three programs in network cache, status node balance, and heavy hit detector. But the P4run programs have faster reaction time since they can be updated at runtime, have no need to reprovision the switch. So we finally conclude that P4runpro achieves runtime programmability for RMT switches. It provides a one-shot combination data plane to virtualize the hardware. It provides an expressiveness primitive set for general-purpose switch programming, and it supports automatic runtime program deployment in a few hundred milliseconds. Our code is now open sourced at the GitHub, and this presentation is supported by the Dengfeng Fund of Tsinghua University. And that's all. Thanks for your attention. Thank you.